T-8 fluorescent fixtures can generate electromagnetic interference, or EMI, that impacts radio reception. Poor shielding in the fixtures themselves allows electromagnetic fields, or EMF, to escape and disrupt radio signals. The magnetic fields generated by the fixtures can induce currents in the radio antennas, causing interference. Proper grounding systems can provide a path for EMF to enter the radio. Here are a few troubleshooting and mitigation steps. Firstly, check the grounding. Ensure that the electrical system is properly grounded. Inspect the grounding connections in the fixtures to make sure they are secure. Secondly, upgrade or shield the fixtures. Consider installing T-8 fluorescent fixtures with improved electromagnetic shielding. Consider using EMI-absorbing materials such as ferrite cores or copper tape to wrap around the fixtures. Thirdly, reduce EMI. Use a surge protector to suppress EMF from other electrical devices. If possible, install the radios in a location away from the fluorescent fixtures or in a shielded enclosure. Fourthly, modify radio antennas. Try extending the radio antennas or using an external antenna to improve signal reception. Consider using a ferrite bead or choke on the radio's antenna cable to reduce EMI. Fifthly, test and monitor the situation. Turn off the fluorescent fixtures while the radios are in use to confirm that the interference is indeed caused by the lights. Monitor the radio reception over time to ensure that the mitigation measures have resolved the issue. Also, consult with an electrician to inspect the electrical system and recommend solutions. Consider using radio frequency filters or shielded cables to minimize the EMI. Electromagnetic interference is a disturbance caused by electromagnetic fields that disrupt, obstruct, or degrade the performance of electronic devices. Sources of EMI include radio transmitters, industrial equipment, and electronic devices. Shielding is the use of conductive or magnetic materials to block electromagnetic fields. Shielding reduces the amount of EMI that can reach sensitive electronic devices. Grounding is the process of connecting electrical equipment to the earth to provide a path for fault current. Proper grounding helps to reduce EMI and improve electrical safety. An electrician can help identify and resolve the source of EMI. They can also recommend and install shielding and grounding solutions. Radio frequency filters are devices that block certain frequencies of radio waves. Radio frequency filters can be used to reduce EMI from radio transmitters and other sources. Shielded cables are cables that are wrapped in a conductive material to block electromagnetic fields. Shielded cables can be used to reduce EMI from electronic devices. Here is a more detailed breakdown of potential causes and solutions. Electromagnetic interference, or EMI, from fluorescent lights can be a frustrating issue. The electromagnetic ballast, especially older models, generates radio frequency noise that interferes with radio signals. Defective or aging ballasts produce more EMI. Shielding is inadequate when fixtures lack proper shielding, allowing electromagnetic noise to radiate freely. Grounding problems can occur when improper or inadequate grounding provides a path for EMI to propagate. Loose connections can also exacerbate the issue. The power quality itself can play a role. Voltage fluctuations and harmonics in the power supply can increase EMI generation. Here are more potential mitigation strategies in greater detail than before. Firstly, upgrade to electronic ballasts. Replace the old magnetic ballasts with modern electronic ballasts that produce less EMI. Secondly, install shielded fixtures. Use fluorescent fixtures designed with built-in shielding to contain electromagnetic noise. Thirdly, ensure proper grounding. Verify that all fixtures are properly grounded to the electrical system's grounding conductor. Fourthly, use line filters. Install AC line filters at the power source of the fluorescent lights to suppress EMI. Fifthly, improve cable shielding. Use shielded cables for the fixture wiring to minimize radiated emissions. Sixthly, add ferrite beads. Clip ferrite beads onto the power cords of the radios to reduce conducted EMI. Seventhly, relocate antennas. Move radio antennas away from the fluorescent lights to minimize direct exposure to electromagnetic fields. Eighthly, use directional antennas. Replace omnidirectional antennas with directional antennas pointed away from the lights. Ninthly, install a dedicated circuit. Put the fluorescent lights on a separate electrical circuit to isolate them from other sensitive equipment. Tenthly, consult with an electrician. Have a qualified electrician inspect the entire system and recommend further solutions such as additional filters or shielding. To elaborate further on grounding, in electrical systems, grounding is essential for safety and electromagnetic compatibility, or EMC. A properly grounded system provides a low impedance path for fault currents, minimizing the risk of electrical shock and reducing electromagnetic interference. For fluorescent lighting systems, grounding is crucial for several reasons. It provides a safe path for fault currents, ensuring that circuit breakers trip quickly in the event of a short circuit and preventing potential hazards. Grounding also helps to reduce electromagnetic interference, which can affect nearby electronic devices such as radios and communication equipment. Effective grounding practices for fluorescent lighting systems involve several key steps. Firstly, each fixture should be connected to the building's grounding electrode system via a grounding conductor. This conductor should be sized according to electrical codes and standards such as the National Electrical Code, specifically Table 250.122. Secondly, grounding conductor should be securely connected to the fixture's metal frame or enclosure using appropriate connectors. Thirdly, the grounding electrode system itself should be properly installed and maintained with regular inspections to ensure its integrity. In cases where electromagnetic interference is a significant concern, additional measures may be necessary, such as using shielded wiring and installing filters to suppress noise. These practices help ensure that the fluorescent lighting system operates safely and reliably while minimizing the risk of interference with other equipment. Focusing on shielding. Inadequate shielding allows electromagnetic fields to radiate freely. This is often due to the design of the fixture or damage to existing shielding. Fixtures designed for low EMI environments incorporate a metallic enclosure or a conductive coating on the plastic components. This enclosure acts as a Faraday cage, attenuating electromagnetic waves. Any gaps or openings in the shielding compromise its effectiveness. Damage such as dents or corrosion can also create weak spots, allowing EMI to escape. Upgrading to fixtures with improved shielding involves selecting models specifically designed to minimize EMI emissions. These fixtures use materials and construction techniques that provide better attenuation of electromagnetic fields. Some options include fixtures with fully enclosed metal housings and those with conductive gaskets around access panels to maintain electrical continuity. Retrofit shielding solutions can also be applied to existing fixtures. Conductive tapes and sprays can be used to create a barrier against electromagnetic radiation. However, the effectiveness of these solutions depends on proper application and complete coverage of potential emission points. When evaluating shielding options, consider the frequency range of the interference. Different materials and techniques offer varying levels of attenuation at different frequencies. Consulting with an electromagnetic compatibility expert can help determine the most appropriate shielding solution for a specific application. Addressing the antennas. Modifying radio antennas can improve signal reception and reduce interference. The effectiveness of an antenna depends on its ability to capture radio waves and convert them into electrical signals. Interference can disrupt this process, leading to poor reception. Extending the antenna can improve its ability to capture weak signals. This can be done by adding a length of wire to the existing antenna or replacing it with a longer one. The length of the antenna should be chosen based on the frequency of the radio signals being received. A longer antenna is generally more effective at lower frequencies, while a shorter antenna is better for higher frequencies. Using an external antenna can also improve signal reception, especially in areas with weak signals or high levels of interference. An external antenna can be positioned in a location with better signal strength, such as outdoors or in a higher location. The antenna should be connected to the radio using a coaxial cable, which is designed to minimize signal loss. A ferrite bead or choke can reduce EMI by blocking high-frequency noise from entering the radio through the antenna cable. This device is a small, cylindrical component that is placed around a cable. The ferrite material absorbs high-frequency energy, preventing it from reaching the radio. The effectiveness of a ferrite bead depends on its material, size, and placement. It should be positioned as close as possible to the radio to maximize its effectiveness. To elaborate on surge protection, surge protectors help suppress electromagnetic fields from electrical devices, preventing interference. Electrical surges and transients can generate significant electromagnetic interference that can affect radio reception. Surge protectors work by diverting excess voltage away from sensitive electronic equipment, reducing the amplitude of voltage spikes and preventing damage. They contain components such as metal oxide varistors, or MOS, and gas discharge tubes, or GDTs, which clamp the voltage to a safe level. When selecting a surge protector for reducing electromagnetic interference, consider several factors. Firstly, the voltage protection rating should be appropriate for the electrical system. Choose a surge protector with a clamping voltage that is below the maximum voltage that sensitive equipment can tolerate. Secondly, the energy absorption capacity should be sufficient to handle potential surges. Look for a surge protector with a high joule rating for better protection. Thirdly, the response time should be fast enough to catch rapid transients. Choose a surge protector with a nanosecond response time. Fourthly, consider the type of connection. Surge protectors are available in various configurations, including wall mount, strip, and whole house models. Choose a surge protector that is compatible with the existing electrical system. Fifthly, look for surge protectors with built-in EMI and radio frequency interference filtering. These filters can further reduce noise and improve radio reception. Surge protectors should be installed at the point of entry of electrical power to the building, as well as at individual outlets where sensitive equipment is connected. Proper installation and maintenance of surge protectors are essential for their effectiveness. Regularly inspect surge protectors for signs of damage or wear and replace them as needed. Choosing the right surge protector and ensuring proper installation can significantly reduce electromagnetic interference and improve radio reception. Focusing on ferrite beads. Ferrite beads are passive electronic components used to suppress high-frequency noise in electronic circuits. They are typically cylindrical or toroidal in shape and made from a ferrite material which exhibits high impedance at radio frequencies. Ferrite beads work by absorbing high-frequency energy and converting it into heat. When a high-frequency signal passes through a ferrite bead, the magnetic field generated by the signal induces eddy currents in the ferrite material. These eddy currents dissipate energy as heat, reducing the amplitude of the high-frequency signal. Ferrite beads are commonly used in a variety of applications to reduce electromagnetic interference. They are often placed on cables, wires, and circuit board traces to suppress unwanted noise and prevent it from interfering with other electronic devices. When selecting a ferrite bead for a specific application, several factors should be considered. Firstly, the impedance characteristics of the ferrite bead should be matched to the frequency range of the noise being suppressed. Secondly, the current carrying capacity of the ferrite bead should be sufficient to handle the current in the circuit. Thirdly, the size and shape of the ferrite bead should be appropriate for the available space. Ferrite beads are easy to install and require no external power source. They can be simply clipped onto a cable or wire or soldered onto a circuit board. Proper placement of ferrite beads is essential for their effectiveness. They should be placed as close as possible to the source of the noise or the point where the noise is entering the circuit. Using multiple ferrite beads in series can further improve noise suppression. In addition to suppressing electromagnetic interference, ferrite beads can also be used to improve signal integrity in high-speed digital circuits. By reducing reflections and ringing, ferrite beads can help ensure that signals are transmitted reliably. The NEC requires that electrical work be performed in a neat and workmanlike manner according to Section 110.12, that electrical equipment be installed according to the manufacturer's instructions and listed or labeled for the application according to Section 110.3, and that equipment grounding conductors be properly sized and installed according to Section 250.130. The NEC also specifies requirements for minimizing objectionable current over grounding conductors according to section 250.6.